Alright, so in the last video we've learned that we can use the cross product to create basically directions around stuff. So really quickly, the logic was if we have points here around some kind of planet or something, some geometry, then we can calculate, and from those points we calculate the direction towards the object. You could also use the normal, it ends up being the same, but you need this direction. And then we add an arbitrary direction on top. In our case, we just added, a direction upwards. And then you can calculate from that the cross product, which will give you a perpendicular direction from those two directions, which in this case was the blue direction. And as you can see, when you do that, what you get is a direction around an object. And in practical terms, this can then look like this. You have any kind of object, and when you run a simulation with those directions you calculated with a cross product, you can calculate a force or a direction around this object. Pretty cool. Now, when we say around an object, actually in nature, it's pretty rare that this happens. So it's good to have that, for space or something like that. But let's think, for example, in terms of water that is supposed to flow around an object. It actually doesn't keep flowing around it. It has usually one direction and then flows around an object. And this is where, when you play around with this, at some point you might figure this out yourself. You realize that you need two cross products. And this is why this is even called as a concept the double cross product. So the way this works is pretty similar to what we've learned so far. The logic here is, again, let's think with a simple circle and some points around that circle. There they are. So we want to calculate the directions for that. And once again, one classic way of starting is to calculate the directions towards the objects. Again, it's totally fine to use the normals as well, but this kind of direction. And then this time, and this is new, we don't take a direction that is arbitrary, where we want to rotate around, but the direction we want to kind of have as the main direction. And then from that, we calculate the cross product, which looks like this. And this is interesting because when you do that, you notice that the cross product will actually change direction, so to say. And this is because technically when you look at the two angles, the red and the green one, they kind of change direction as well. So the red one is sometimes on the left side and sometimes on the right side. And this results in a different direction of our cross product. So this is actually intentional because this is the trick for the next step. Because now what we do, we take this, only the cross product that we just calculated, which by itself is kind of useless. And then we add again the towards that we already have calculated before. And now we have again two vectors that we can use to create an additional cross product. And this is where the double cross product comes from. And this is now the pink one or the purple one. And it's not obvious at first, because at first it looks like, okay, this is just another vector around the sphere. But when you look closely, it actually isn't. You have some directions that go around on the right side and some directions that go around on the left side. They do not keep moving in the same direction. How we would use the term in everyday life, they flow around the object. And this is what you can do with a double cross product. If you look at this in another example, so here I try to show this with more points and coloring the directions differently so you can see it better. And remember, the direction that we have here from our perspective upwards or, in the back is based on the first vector that we chose here when we decided that this should be our flow direction, so to say. The kind of the first cross product that we created used that vector, and then the end result of this was then the double cross product, which again is easier to visualize in this picture. And what we can do with this is something like this. Let's say we have a couple of objects like rocks or something, and we have points that we want to kind of move through this field of rocks. By default, they would just, flow through it. But if we use a double cross product, we can create a direction that kind of calculates the, direction around an object without constantly keeping to rotate around the object, but really flowing around it. And here you can see the idea. You can, create flow logics with that yourself and force the points to move around objects in a more or less natural way. Now, of course, if you wanted to do a real fluid simulation, you would use Flip, but this is only meant to kind of visualize the concept and the idea behind it. Let's do this together now that we've seen the theory behind it. And let's actually use the example we just saw. The setup is relatively straightforward. We have a grid and we scatter points on it. This is where our rocks will end up on. And we, create our rocks the good old way with a mountain node. It's always the same node here. And I randomize the direction with an attribute randomize orient, which of course has 4 dimensions. And then it looks like this, nothing too special. Now let's set up the PopNet. And we use this, of course, as an input for our PopNet. And we want the points to emerge somewhere here. There you go. This is my original grid that we have our rocks on, and this is where I want to emit the points from. So the good news is the PopNet will right away scatter points on it, but for now they're really just scattering, not moving. There are multiple ways of doing this actually. We could create our own velocity field to drive our points with the same result, just feeding the directions into a velocity field. But it's easier actually, just for now, if we simply override the velocity of our points directly. So all we use here is a simple pop wrangle inside of our simulation, of course, so that we can change the velocity of our points while they're moving, basically. So let's test this first, just to be safe that our assumption is actually correct, that we can move our points that way. So while you can't see it, from left to right is positive x. So let's add a vector to v to see if our points are moving at all. Okay, so that looks good. We can actually control the velocity of our points. Nice. So before we move on, let's actually start, and it is a bit tricky to show this. So I think I will pin the outside and then go in and write the code, and then we can have a better idea what's going on, hopefully. And the first thing before we actually set the direction is we need to calculate it. And we said we need a couple of vectors. The first one is, take this point, yeah? He needs first a direction towards the object or the normal of the object. I will keep working with the point towards the object because then we don't have to create the normal. So we need a point, and I call this closest point, so that it's easier to understand. And with that is actually, no, I call it closest P because it's meant to be a position. And to find the closest position on a object, of course, or multiple objects, is of course minpos. So now the problem is minpos needs an input, and be careful when you work with pop wrangles. By default, you have to actually set the inputs here. And unfortunately, for some reason, they're turned off by default. So you have to assign the inputs. What I usually do is I simply set this to the same as we would expect, and that is first on first, second on second, and so on, because this is the most natural. So the input now, remember that you can put it wherever you want, but we put it in the last input. I have no idea why. That was just my intuitive decision. So this would be the third or fourth input, and then of course we need our current position. So the thing is, I just realized while this is not bad, it's actually better to put this into an attribute which allows us to actually double check what comes out of our code here, because we can always check if closest P, for example, has data this way. This is much better for debugging, so let's keep working like that. So that seems to work. And now let's calculate the direction towards that point. And I actually will call this towards. And to calculate the direction between those 2 points, it's of course the closest point we just found minus our current position. And I always mix the order up. If you do it the other way around, you will notice that because your vector will be away from the object. So let's see if that worked. If we actually had a towards attribute, there it is, we have it. So let's try to visualize that. And I could go outside and then click on the attribute, but this time I do it manually actually. What we want is we want to see the vector towards. Remember, this only works because we're looking from outside right now. So let's switch this to vector. And there you go. It is actually towards the closest object, not away from it. So we were right. That sounds good. I will right away tell you there's one thing that is very important. You might know what I'm going to say. Always normalize your directions. So let's make sure we don't forget about that. So there we go. Now we have the towards vector. The next vector we need this is interesting. Now, as we've seen, we need the direction we want to move in, which is again positive x in my case. So let's call this dir for the main direction. And we just set this to 1, 0, 0, which is normalized and also, the main direction we want. And now, of course, we calculate the first cross product. So let's actually call this cross1. And that's pretty simple. And we just create the cross product between the towards vector and the dir vector. And actually now I realize it's a good idea now to actually show all those. So first of all, the towards turn into red. Then we add another one that we just defined and call it dir. And since I made this green in our theory, let's do this again. Here you can see, yeah, pretty straightforward, exactly what we expected. And now the interesting thing is, let's have a look at our cross product that we just calculated. And let's turn this blue. And I don't think we can see this just yet. Actually, we can't see it at all. Oh, cross1, we called it, exactly. There you go. Oh, we can see it yet. That's nice. So as you can see, and that's interesting, sometimes this cross product is upwards and sometimes it's downwards. And that's perfectly normal. This is actually what will later define how we move around the object. So let's move on. Now that we have our first cross product, we will still need the towards vector. So let's keep that, but the dir vector will from now on be useless for us. This did his part. So let's create the second cross product. And this is now pretty simple. We just have to remember we use the cross product 1 that we just created. And then we take the towards direction again. And what we will get, we can visualize with a new visualizer. So cross 2, there it is. Let's turn this, what did we say, purple or pink, it's easier to see. And to test this, let's just set the velocity to this new cross product that we just created. And let's play this. But you can see it works. The only problem now is, yes, it flows around the first object it finds. And when you're lucky and the point then kind of moves in the area of the next object, then you will have a more or less continuous move. But you can see it's not super stable. It doesn't keep flowing properly. So what you might have to do, and that's totally normal, you just add a little bit of this direction you already had to the movement. And now you should have the direction, if you rewind, of forwards movement and an around movement. But then you have, of course, the problem that the points will sometimes be too fast and will move through the whole thing. So this is now a little bit of a balancing act and it depends on your case. But what we can do here is we just use a multiplier for both velocities. So I call this around strength and directional strength. And of course, sure, we could use the objects as collision objects and then it will never go through it. So that might be a good idea. But having an additional, way of controlling the whole thing, maybe let's set the directional strength to 1/3, is either way pretty helpful. So, and maybe, if you don't want to have something like that with a massive gap, then you can just lower the around strength and then more points will move towards it. This is then how you balance the directions out. So let's actually add the rocks as a collision object. And since we already have it, this is, what we're seeing right here. There it goes into the last input. And let's make sure actually we only see the particles. Yeah, it's easier to see then. And here you can see there's now actually a collision happening. So for example, there you can see it. What you can always do, of course, is adding a bit of a pop force to add a little bit of noise. It's always a good idea, even if you drive our stuff with velocities. It's never a bad idea to add noise to your simulations. And then, we have something like that. It's not perfect, but again, it's a great example to explain the concept. So yeah, as you can see, if you want to move something around an object, then you can use the concept of a double cross product. It's really just changing the logic of how to calculate the right directions. And what it boils down to is that just like before, we calculate the directions towards an object. And now that's interesting. We add a direction that our flow should be. When we create a cross product from that, we get something surprisingly weird that is a direction that goes into different directions, which is the source for the next step where we add our towards direction again and now calculate a second time a cross product, which is why it's called a double cross product. And then we get this result. We have directions that flow around an object, which is easier to see when we look at it here. There are a lot of different use cases for this concept, but usually, some fluid-like thing to flow around something is a pretty common use case for that if you don't want or you can't use flip simulations as an alternative. So I hope this is helpful. Thanks very much and see you later. Cheers.